He bolded all of the things that he wrote in, and I had to like cut out like half.
Yeah, that's. I don't know. He writes down a lot of good information, but he has
A lot of it.
well. No, I got a lot of information. He's got a way with words. It's
It is a
it's
way. It's a way to do words.
it's the wrong way, but I'm not that much better. I repeat myself too much. I reiterate the same things. I go over the same facts too much. I say the same thing. So that's my
little redundant.
Today, we return back to our lecture, the first session, and continue our discussion. So. Wait a moment until this active. Show. Okay. Okay. So we go back to our equation, or governing equation, and at this stage, I introduce you some mathematical descriptions. So we have three parameters, three mathematical parameters. Three key operators: gradient, divergence, curve. Gradient, divergence, and curve. Gradient is something that increases the rank of the operator. So, gradient, I should put a vector over all of them. Gradient, we are interested in velocity because we are in fluid mechanics. We are mostly interested in velocity. Gradient of V. What is this? And V is the velocity vector, Ui plus Vj plus Wk. So, gradient of V is a tensor or is a matrix partial u partial x partial u partial y partial u partial z. Partial v partial x partial v partial y partial v partial z. Partial w partial x partial w partial y partial w partial z. This is gradient of v. So gradient of a vector is a tensor. V has three components, is a vector. Gradient is a tensor. So 3 by 3. I want to introduce you a new notation that is called index notation. Does any one of you heard the name of index notation? Rather than, rather it is a vector notation, it is a vectorial notation. So when you go to the higher level, your master level, I know some of you are in accelerated master or go to the master, interested to go to master. So some intelligent guy told, rather than writing in this way, he told gradient of B is equal partial BI partial xj. Okay, index notation. How to spell out? Take a look at me, I don't write, I just explained to you. How to spell I this? First, I, 1, put I1, V1 is U. Rotate J from 1 to 3. Second, I2, J, 1, 2, 3. Third, I3, J, 1, 2, 3. So you put I1, V1. V1 is U. Then J1 to 3. X1 is X. X2 is Y. X3 is Z. Okay? Vector X has three components. Xi is X. X2 is Y. X3 is Z. Okay? Then go put I equal to. I equal to is equal second component, V2. V2 is a small v. V x1, x2, x3. This is called index notation. I want to make you familiar with advanced mathematical operator when you go to the advanced classes, rather than, you see, I need to spell out this grad V in a matrix, in a tensor. Now I can write partial V, partial xj. Yeah?
So I is the rows and J is the columns.
Exactly, yeah. I is the corresponding to the V, J correspond to the X, Y, Z. We cannot say I is row, J is column. We should say I is correspond to V component, J correspond to the X component, vector X. V is a vector, X is a vector. X vector is X, Y, Z, V vector is U, V, W. And I later write you what is the divergence in terms of this, and what is curl in terms of index notation. I will later tell you. Let's return back to gradient. Did you have a course in linear algebra? And in that course, are you familiar with the transpose of a matrix? So it is a matrix, 3 by 3 matrix. So we can transpose, it is gradient V transpose. Transpose means put the row in column, okay? It is the transpose of the tensor or transpose of the matrix V. It is the transpose. Okay? We define S as rate of strain tensor. Rate of strain tensor equal grad V plus grad V transpose divided by 2. It is the rate of strain tensor. The student who has solid mechanics with me, or you had a course in strength of material, you know that a strain is the displacement, normalized displacement. In fluid mechanics, we are interested in rate of strain. So rather than displacement, rate of displacement is velocity. So if you add this one and divide by 2, you get rate of strain tensor of a fluid. If you compute omega as gradient tensor minus gradient transpose tensor It is rotational rate of rotation or rotational tensor. Okay, as I told you, aerodynamics is the paradise of complex mathematical operators. So you should know some mathematics. Later we will use this mathematics in our relations, in our equations, in our simplifications of the flow analyzers and so on. So what did I do here? I start with the gradient. I spell out gradient. I wrote gradient in index notation. I computed gradient transpose matrix. And then I define it for you, rate of strain and rotation tensors. So everything, strain means displacement per time over initial length. Rate of strain is a function of velocity gradient. Rotation, if you rotate an element of fluid, is a function of velocity gradient minus transpose of velocity gradient over T. Okay, let's go to the divergence. Gradient is a bit difficult, but divergence is very super simple. You have divergence on the PowerPoint. Divergence of V, or you have gradient. You have gradient on the. Okay, one question. Why my gradient on the board is a tensor? The gradient on the PowerPoint is a vector. You see, gradient of P is partial P partial xi, partial P partial, yeah?
Is it because it's a scalar?
Exactly. P is a scalar. Gradient is an upgrader, upgrade you. If you apply gradient to pressure, pressure is a scalar. So it creates a vector. Partial P partial xi, partial P partial yj, partial P partial zk. Gradient is an upgrader. What you apply on the board, I apply gradient, which is an upgrader, to a velocity, which is originally a vector. So it upgraded the vector to a tensor. It upgraded a scalar to vector. It upgraded a vector to a tensor. Okay? So more complex. So gradient of pressure, and interestingly, in the momentum equation that we want to drive for you, we have both gradient of velocity and gradient of pressure. Okay? Gradient of velocity and gradient of pressure. On the board, I just write for you in the Cartesian coordinate. Here on the PowerPoint, you see a gradient of P in the cylindrical and spherical coordinate as well. You may have some problems in cylindrical or spherical coordinate, okay? For example, when we have source and sink are in cylindrical coordinate, not on the Cartesian coordinate. So you require to know these two, okay? In the cylindrical, in the spherical coordinate. You don't need to memorize them, you just know to know the formula. Okay, let's go to the divergence. Divergence is super simple. Divergence is a downgrader. It cannot be applied to a scalar because a scalar is the minimum. The minimum that the divergence could apply is the vector. So divergence of a velocity is partial u partial x plus partial v partial y plus partial w partial z. On the board, you can see divergence in cylindrical and spherical coordinate as well. Does anyone remember the continuity equation? The continuity equation I derived 2 sessions ago. The continuity equation was like this. Okay, it was the original continuity equation. Then I converted the second term to a divergence term. Then I concluded that when an integral is 0 in any condition, the integrand, what is inside the integral, should be consistently 0. I assume the flow is steady. Which term vanish? For a steady flow, which term?
Velocity,
No.
acceleration,
Which term? Yeah.
dt.
dt, yeah, is vanish. Vanish. I made another extra assumption. The flow is incompressible. Which term is constant?
Rho.
Rho is constant. Okay, so what is the result? Okay, now let's solve an example together. Because you see, I taught a lot of course, but I didn't solve you an example. I designed the example from my mind now. I don't have any paper. Example. Assume 2D income flow. If we assume income, the first term also vanishes because it is density. When the income density is constant. U is 2x. Find V. We have a 2D flow. V is equal 2xi plus Vj. The question asks me to find V. What should I do? Take a look at the board. Take a look from very beginning and tell me what should I do. I don't know the V component, but I know the flow is incompressible. What should I do? Yeah,
Set it equal to 0 and do divergence.
exactly. I should go to this equation. Pay attention. If rho is constant, divergence of V is 0. Okay? So I don't know V, but I know that divergence of V is 0. What is divergence of V? Divergence of V in 2D. Tell me please.
Du dx plus dv dy.
Partial U partial X plus partial V partial Y is 0. What is equal partial U partial X? What is equal that? Yeah?
2.
2. So, partial V partial Y is equal minus 2. How to obtain Y? Partial V partial Y is minus 2. How to obtain V? Sorry. How to obtain V? Yeah?
Integral.
Integrate. I integrate this. Minus 2y plus cx. A constant which can be function of x. Okay? Integral of minus 2y, v is equal minus 2y plus constant function of x. Why I added this constant function of x? Yeah?
It was unbounded. The integral was unbounded, but why didn't you add y instead?
No, because I know partial v partial y is equal minus 2. So when I use minus 2y plus cx, I should reach to this equation. When I take partial, the partial of this is 0 because it's function of x. Okay? When you take integral with respect to y, you can have a constant in your equation, function of x. In order to find this, the question should be should give you a boundary condition. Find v. Assume assume v 0, 0 is x. No. V 0, 0 is 0. It should have a value. X is 0, it is 0. Okay? I need to clean here. So V is equal to x I minus 2y j plus cx. Okay? I put 0 and 0. When I put 0 and 0, V should be 0. So 0 at so 0 is equal 0 minus 0 plus C is 0. It is B. Is it clear? Anyone has a question or comment? Please stop me and ask the question. Yeah.
Why does it become CX and not CY, or does it not matter?
And it matters. If it was Cy, it gives a derivative with respect to y. How I reach to this equation? I have this equation. Partial v partial y is minus 2. Why? Because I have divergence. Do you agree? I have divergence equals 0 because flow is incompressible. So partial u partial x is 2. Partial v partial y is minus 2. So v is equal integral of minus 2 dy. V is minus 2y plus a function of x that doesn't give any derivative when I take derivative with respect to y. If it is a function of y, it gives minus 2 plus c. But the question says us minus 2, not minus 2 plus c. Okay? So it is a function of x. It is a trick in 2D integration. Okay? When you integrate in one direction, I integrate in one direction. Add a constant on other direction to compensate for the term that doesn't appear on the derivative. I will give today, when I go to my office or I go to home, I will give you your first homework. And in your first homework, I tell you something like this, but maybe in cylindrical or spherical coordinate. Okay? In cylindrical or spherical. Not 3D, 2D, because 3D is a bit challenging. 2D, if I give you in cylindrical, so ignore Z, so you should solve this equation. I tell you a flow is circular and diverge, so it is incompressible. When I tell you it is incompressible, you conclude divergence is 0. Okay? Then put the left side equals 0. On the right side, I should give you information about one term. I give you information about one term. You solve this equation, find the missing term. Okay? So it is very easy. But the integration may be difficult. I try to give you a homework that you require using MATLAB for integration or Python using integration, because you are most of you are in the last semester in your bachelor, yeah? So you should level up compared to the last, and you shouldn't solve this simple question. It is just for the class. The professors usually solve the simple question in the class and ask you to solve the difficult question in the homework, and most difficult there in the exam. Yeah, it is the life. Okay, it is divergence. Now let's go to the third one, which is curl. Curl of V is the cross product between gradient vector and velocity vector. we show curl by omega. In 3D, it is I, J, K, partial x, partial y, partial z, and u, v, w. How to compute the curl from this matrix? Do you remember from linear algebra? Exactly. First, omit the first column and the first row. Compute the determinant of the remaining. So it is equal curl of a vector is a vector. Okay? Gradient of a vector is a tensor. Divergence of a vector is a scalar. Curl of a vector is again a vector. So I have again a vector. Partial w, partial y, minus partial v, partial z in I direction. Partial u, partial z, minus partial w, partial x in y direction, j direction, partial v, partial x minus partial u, partial y in k direction. If the flow is 2D, only the last term remains. Okay, I give you a second, I give you a minute. Please solve this example and tell me the answer. You solve? Okay. You solve? Okay. I give you a few more minutes and then we solve together. Or I can ask someone to come to the board and solve for us. You come, yeah. Here the child.
Which is the non thing.
Okay, case one. Please explain what you write and what you solve. Just explain to the
Case one?
yeah.
Okay.
Explain to the student.
Alright, so we can start with case one up here. So I guess what I did is looked over here for 2D flow and then try to figure out the determinant from here. So dv dx is going to be 0 because no x term. Similar for this term, no y's are 0 in the u at least. And because of this, flow is irrotational, so it's not this one. And then here, if we do the same method, dv dx is going to give us -2, and then du dy is going to give us a 2, but we subtract. So we have a non-zero answer for the curl, so we have rotational, so it has to be case 2. And then if we check over with case 3, we get similar to the first case where dv dx can be 2 and then minus du dy 2. 2 minus 2 is 0.
Please
That's
write.
what I know. So flow is irrotational, so can't be this either. So there you go.
Okay, thank you. So you simply need to compute the last term here, which is partial v partial x minus partial u partial y. So first term, first velocity, great. So the first flow is very good, very positive flow. It is not only incompressible, it is not only incompressible because the divergence is 0, but also it is irrotational. Okay? It is irrotational because the curl is 0. The second flow is okay. Second flow, is it divergence free? Second flow, is it divergence free? Check the divergence free means divergence is 0. Then divergence is 0. The flow is called divergence free or solenoidal. Okay? Second flow, divergence free or solenoidal? No?
No.
No?
It's
Partial u partial x, how much?
0,
Partial v partial y.
0.
0, it is divergence free. But it is rotational. Okay? So the first flow, divergence v, 0, curl v, 0. Second flow, divergence v, 0 solenoidal but rotational. Curl v, non-zero. Third flow, divergence v. Third flow, divergence v. Yeah?
Non-zero?
Non-zero? Partial u partial x.
Oh, yeah, so it's 0.
0 partial v partial y. 0. Divergence v 0. Curl v 0. Okay? So the flow can be solenoidal, the flow can be non-solenoidal. The flow can be divergence free, the flow can be rotational or irrotational. Make sense? Is there any ambiguity? If you have any question, don't be shy. Interrupt me. The class is a place to learn everything, okay? You shouldn't go in home and spend 2 hours to understand. It is a place that you learn. I always solve an example and then give you homework. Even though the homework will be more difficult, but the basic is the same, okay? So you understand this, okay? But maybe in the homework you have something in the cylindrical coordinate rather than Cartesian. Not so simple as 2x, 2y, more complex equation. But the principle is the same, okay? The principle is the same. I want to mention, I wrote for you gradient in terms of index notation, but I didn't write for you divergence and curl in index notation. So let me clean left. So aerodynamics is the science of mathematics, okay? You should know very advanced mathematics in aerodynamics. We will work a lot of advanced mathematics in aerodynamics. So it is a paradigm of mathematics in aerodynamics. As we proceed further, you understand better and better complex mathematics. Divergence of V is equal partial V I partial xi. Gradient of V was partial Vi partial xj. Now it is Vi xi. When you have a repetitive index, you don't need to rotate over parameters. You just need to write in this way. Put I equal 1. V1 is u. Put x equal 1. x1 is x. Plus V2 is V, a small v. X2 is y. V3 W. X3 z. That's all. So we put I equal what? In both numerator and denominator. We put I equal 2 in both numerator and denominator. We put I equal 3 in both numerator and denominator. That's all. Curl V is a bit complex. I just write for you. I don't want you to go. Curl V in index notation is equal partial Vk partial Xj epsilon I J K. epsilon ijk means like this one, like the same as the tensor. It is Levi Chiotina. I'm not sure if I write the name. It is Levi tensor. You can do a search about this, but it is not in our concept. I would like to tell you something more mathematically. Curl of gradient is 0. Divergence of curl is 0. For any function, curl, if you take a gradient of a function, then take a curl, it is 0. If you take a curl and then take a divergence, it is 0. So divergence, curl, gradient. This of this is 0. This of this is also 0. Okay? Yeah, question?
I'm just curious, so cross product, it matters like the order of things, so
Yeah,
you-
it matters. It
so
matters.
if you have the gradient or if you swap the two terms on the first one,
It matters. It matters.
yeah, so it wouldn't be 0 if you swap the two terms then on the curl of the gradient.
Yeah, it is curl of gradient of any function. But gradient of, if you put gradient of curl of something, no.
Okay.
No. Yeah, I didn't put this part. I just follow this. Okay? Divergence of curl, curl of gradient. But gradient of curl is not 0. So, I taught you 3 operator: divergence, curl, gradient. Divergence is related to dilatation of a fluid. Do you know the meaning of word dilatation? Dilatation means, the volume expand or volume reduces. So divergence is something about volume. Curl is something about rotation. Okay? Take a look. Which flow has a curl? A flow that velocity component are function of opposite direction. The first flow, velocity is in x is a function of x. No curl. 0. Second one, velocity of x, u is a function of y. It is a rotational flow. So it has rotation. Are you familiar with the Couette flow? Did you ever heard the name of Couette flow or Poisy flow? No, in fluid mechanics? Okay. So assume you have a channel. The top wall moves with the velocity of v. The bottom wall is stationary. The flow varies linearly between 0 to the velocity changes linearly between 0 and v wall. Okay? Velocity on the bottom surface is 0. Velocity on the top surface is v wall. Okay? This flow has a velocity in this direction. Velocity in x direction, what is the name of velocity in x direction? U. Okay? U is uy. Make sense? Why is uy? Because on the bottom surface it is 0, on the top surface it is v wall. This velocity varies linearly. So u is equal v wall y over h. This is h. This is y. When y is 0, u is 0. When y is h, u is v wall. Make sense? This flow is rotational. Why this flow is rotational? Yeah?
This curl is not zero
Why curl is non-zero?
because they depend on the opposite variables.
Exactly. U is the x velocity depending on y. This flow is rotational. What does rotational means? I have velocity here, v wall here. Take a look. 0 here. For example, v wall over 2 here. V wall over 2. Flow is rotating. There is a vortex. The flow moves from where the velocity is higher to where velocity is lower. This flow is rotational. This is called Couette flow. A flow inside the channel where the lower wall has a 0 velocity and top wall moves but v wall. This is a let's say rotational flow. Okay, let's go. I use the board as I could. Let's go to the PowerPoint. We have divergence of v equals 0. Divergence of v in the Cartesian coordinate. Here you see in the Cartesian coordinate divergence of v. Here you see divergence of v in the cylindrical coordinate, and here on the bottom you see divergence of v in the spherical coordinate. Okay? So I may give you a homework that you need to solve in a spherical coordinate, and you need to, for example, I give you a velocity component in the r direction, and then assume the flow is doesn't have any direction in phi. In the sphere, we can have 3 directions: r, theta, phi. R is the radial, theta is in plane, phi is in space. okay, in a space direction. If you assume a sphere, the phi is from 0 to 360 degree. But theta is on the plane. Assume we don't have anything on the space, we have just in the r direction and in theta direction in plane. So if I give you VR, you can find v theta, assuming that the flow is divergence free. Okay? I can make the problem more complex. I tell you the flow is not divergence free, but I measure divergence to be equal 5. Then instead of divergence free, you put here 5. Okay? Because here I clean here. We obtain this velocity by assuming the flow is divergence free. Divergence is 0. But if I have a tool that can measure the divergence, I can report you the divergence, and then you can solve this equation and find, let's say, the missing term, missing component. Okay. There are 3 rules in the, when I was a student in Mathematics 2, you have 2 mathematics. You have 2 mathematics in the first year. Yeah, in Mathematics 2, our professor taught us this relation, and we used the first relation for, not the first one, we used the second one for the continuity equation. There are 3 rules. The first rule says that, let's start with the second, that we use it. The second rule. The second rule says that integral over a surface of a vector dot surface element is equal integral over a volume of a divergence of that vector over volume. We use this relation and converted in continuity equation. We have rho v dot es. We converted that to integral over volume divergence rho v volume. Okay? This is the second rule. These are the mathematical rules. I told you fluid mechanics is the paradise of applied math. A lot of professors in fluid mechanics are those who are expert in applied math. They know very complex mathematical equation and where to find, because when you do mathematics, you may have some hypothetical object to work on. But in the fluid mechanics, you can find some real application. When this guy find this identity, they don't know where it is useful. But in the continuity equation, it is useful. Help us to write continuity in terms of integral per volume. So it is the first rule that we use. We use 2 other rules as well. This rule on the top, we will use it for curl. Curl. You see, curl of a vector dot ds over a surface. Curl of a vector dot ds over a surface. The integral is equal line integral of the same vector over a line. The small ds is the element over the line. The big ds is the element over the surface. We will use this relation for vorticity and for, what is the name of that? When we integrate vorticity. When we integrate vorticity, we use this equation. It is the curl of the velocity. So it is used in the line integral. Circulation. Okay. The name of this is circulation. What does circulation mean? Assume it is our surface. I have a vortex inside this surface. I integrate, you see, I integrate over this surface and find the accumulative contribution of this vortex inside this surface. So it is used for obtain circulation. Later, I will give you some example. I will solve you some example on this line integral and surface integral. The third one, which is used in the momentum equation, integral, surface integral of a scalar on the left. P is a scalar. Surface integral of a scalar is equal gradient of a scalar dv over volume integration. Okay, now it speaks about the physical meaning of the divergence. We skip this. Okay, continuity equation. I drive it for you, the continuity equation. It is just a review and go to the momentum. It is the last term is the continuity equation, and then we go to the simplification of the continuity equation that we performed so far. Let's start momentum equation. We have a few minutes and we can just discuss about momentum equation. Momentum equation is an expression of F equal ma in fluid dynamics. Okay? In fluid dynamics, we want to express F equal ma. F is the forces. What are the forces over the fluid? The forces over the fluid are forces. Volume force, surface force. Volume force are like weight. Take a look at my body. Assume I am a fluid. I have a weight. The weight of every cell of my body acts on that cell, like the weight of this acts on every cell. So it acts over entire volume of the chalk, of me, of anything. So assume it is fluid. The mass of the fluid acts on every single element of the fluid. But assume this chalk is a fluid, the surface forces act just the external surface of this chalk. Surface forces are two forces, pressure force and shear stress force. Volume force, weight, surface force, P, tau. Pressure force, tau. Assume it is our control volume. Okay, this is our control volume. Pressure act normal to the control volume. Can anyone tell me what is the direction of normal vector of this surface? What is the direction of normal vector? This surface has a normal vector. Remember at first session, this door has a normal surface, normal vector. I plot the line. What is the direction of normal? Yeah,
Facing outward?
Outward, yeah. It is the normal vector. So pressure is always in opposite to the normal vector. Normal vector of surface is a vector pointing outward. So the surface force due to pressure is surface integral minus P ds. It is the surface force. Volume force is volume integral rho f dv. F is force per unit mass multiplied by rho dv to get the force over volume. So forces are minus PDS plus rho F dV plus F viscose. Okay, that is sufficient for today. On next week we will continue our discussion and I will give you your first homework later today. Thank you. See you next week. You take the course?
Yes.
Okay.
Thank you.
Thank you.
No, yeah, no, I saw that.
In the campus. We have.
Yeah.